recording. So for 5.2 number 1, this is one where I have an integral from 0, well at least this problem is set up from 0 to pi over 2, and I have 2 times the cosine squared of x dx, and here they say that n equals 4, and also it says that I need to use the midpoint rule to evaluate the approximation. So I'm thinking of this as M4. Really, this is just sort of a review problem from some of the things that we did from the last section, so maybe I don't want to go through all of the pieces. I guess I have a calculator here. I'm going to graph, well, what does this look like? Let's go into my graphing mode. And I say that this is the function, oh, this is maybe one piece. Maybe this is why it was a problem. That this notation, cosine squared of x, is exactly the same thing as the cosine of x all squared. That this isn't some other function that you might think, I don't know, that's a notation that can be confusing. But if I go into my calculator, I can graph 2 times the cosine of x, and I'm going to end this parentheses, and that whole thing's going to be squared. And then when I graph this, I see that it's a squiggly function that always stays positive, which makes sense because outputs of squared functions are always positive. And it's squiggling, I don't exactly know where that intercept is. I guess I could solve it's when cosine of x equals 0, which is right at pi over 2. So this is pi over 2. This is 0. It's squiggling downwards. I'm going to break it up into 4 different pieces, find the midpoints for each of these places, and compute the heights. Maybe my one comment, I'm going to draw a picture to represent this without going through all of the computation because I'm too lazy. But one comment is if you were doing this on a calculator, make sure that your calculator is in radians. In general, we'll never use degrees in this class, so you can change that by going into your settings, which I think is mode, yeah. And if I scroll down, I can change between radians and degrees in my mode. This is for this particular TI. If you have a different type of calculator, you'll have to do some hunting. But yeah, so this is a review problem, and I think if you have problems with that, you can send me a message or something, because I don't want to write down all of the heights of all of those things. Done. Look, let's cross that off the list. Nice. So let's look at number 6. Number 6, I like this problem. In part, it's a review of piecewise function notation, which is something that I think gets skipped over, and we can definitely talk about it more. So we're looking at the integral from 0 to 5 for our function. In this case, we have a piecewise function given by f of x equals 3 for x values that are less than 3, and then our function is exactly equal to x for x values that are greater than or equal to 3. And again, your number 3 here might be different than the numbers that I have. But because we're asked to be able to estimate this integral, we're going to have to set this up. We're going to have to draw the picture of what this function is representing. And the easiest way that I like to do it, I'm going to do a little scratch work. In my head, I think of this as a number of different functions, and I put them all together in the end. So I think of this as the function as y equals 3. It's one of my functions. And then maybe I'll call that y1 equals 3. And then I have another function, y2 is equal to x. This is my thought bubble. And it's going to be equal to 3 whenever my x values are less than 3. So let's draw a picture of that. Here's my x-axis and my f of x-axis. So my function y equals 3, that's going to be just a straight line. It's going to be the straight line where my y values are exactly equal to 3. And my restriction here is telling me that it's only going to be the line y equals 3 as long as my x values are less than 3. So as soon as I get to an x value of 3, I'm going to stop. And I've graphed the first piece of this function, the top piece. For the next piece of the function, I'm going to look at my next function. My next function is the function y2 equals x. And this is just a line. This is the most basic line and also one of the hardest lines to recognize that it's actually a line. If I think in my head, this is the same function as 1x plus 0, meaning that I have a slope of 1 and an intercept of 0. So it's going to be a line. I'm going to draw it sort of dotted along here. The entire line would look like this, right? But we don't want the entire line. We only want the piece of the line for the x values that are greater than 3. So I'm going to fill in for where my x values are greater than 3. And it happens that these two pieces hit one another. So this is a continuous function, but you can have other piecewise functions that aren't continuous. So what was our original problem? We drew this graph of this piecewise function. Now we're asked to integrate from 0 to 5. And graphically, in this case, that's going to be the area under the curve. Maybe I'll shade this, do a nice shading job. And there are a number of ways that we can find the area under this curve. For me personally, I wish I had a different color. Let's see if I have another color in my bag.
There should be.
Because I have black. Oh, nice. Yeah. So, yeah, let's break it up. Here's the green piece. You can do it however you want. I'm going to break it up into a rectangle and a triangle because that's the easiest areas. Because then this rectangle has a base of 5 and a height of 3. So it has a total area of 15. And then this upper triangular part has an area of 1/2 of the base, and in this case the base is the difference between 5 and 3, which is 2. And the height difference is going to be the difference between 3 and 5, which is also 2, which is 1/2 of 4, which is 2. So that means my total area is going to be and that's just for the numbers that I had in this problem. If you had different numbers here. Yeah. Cool. It's a good problem. I like that problem. Yeah, so the next problem that I want to talk about is 15.2, number 9. Let's see. Yeah, so for this one, we're given the fact that the integral from 1 to 3 of e to the x dx is equal to e cubed minus e. And really, these are actually just number values, and that's one of the things that I think makes this problem look confusing. It's telling us that this crazy integral thing is exactly equal to e cubed minus e, which it is, if I wanted to get a decimal approximation, I can plug this into my calculator and see that where's my e to the 3rd minus e to the 1st. So this is about equal to 17.367 ... In general, I don't like decimal approximations, but in this case I think that it gives you an idea that this integral, this big chunk, is just equal to some number. That's just the setup. And then what do I want us to do? We're going to integrate from 1 to 3 of the function 3 times e to the x plus 2 dx. And all we have to use are properties of integrals. So I'm going to, what do we want to do first? First thing I'm going to do is pull the constant out front. That this is multiplied by 3, that's going to be the same thing as 3 times this integral. 1 to 3 of e to x plus 2 dx. So that's one of our properties of integration that I can pull the constant out front. But that's not good enough because this inside part is still e to the x plus 2. And this is where we have to actually apply a rule of exponents. This is something that isn't unique to integration. This is the same thing as e to the x times e squared. And I was able to break up this exponent sum into the product. Why am I allowed to do this? And this is one of the things that I think I'm going to do a little thought bubble because it's one of those things that people memorize or forget that I think is an important thing to remember. So let's say that I had, like, what is e squared times e to the 5th? Well, that's e times 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 e. Whew. Well, that's a lot of e's to write out, but how many e's are there total here? Well, that's just e to the 2 plus 5, which is e to the 7th. All I'm doing is repeated multiplication. So repeated multiplication I can represent as the additivity of exponents. I say all that stuff. What does that give me? So I've rewritten this. This gives me actually something really cool, that this e squared, again, is just some number. I can plug it into my calculator and it tells me that, oh yeah, e squared is equal to 7.38. So this is a constant that I can also pull out front. And I'm left with 3e squared, integral from 1 to 3 of e to the x dx. And now we're home free. Now we're home free because we know that this integral is exactly equal to e cubed minus e. So I'm going to do a substitution, and I'm going to leave my constants out front, and I'm going to replace this integral expression with what I was told it was equal to, which is e cubed minus e. And if I wanted to, I could use the distributive property and multiply this out, and I would get 3e squared times e cubed is e to the 5th because of the property that we just talked about, minus 3e cubed. And I could plug that into a calculator to get a decimal approximation, but I think that WebAssign likes it more when I just plug in exact values. Cool. Then one more in section 5.2, I want to talk about, is it number 11? Yeah, I like number 11. So I'm going to sketch by hand the graph that they have for this. -2, -4, and I think everybody has the same graph for this. And we're told that the graph of f bounded by the x-axis has an area of 3. So that if I were to sum up each of these pieces, the total area would be 3. And I want to know what's the value of the integral from -4 to 2 of this crazy thing. F of x plus 2x plus 3 in this case, dx. That's interesting. So it turns out that we don't actually even need to use the fact that area is 3. Oh, I think that they're leaving out an assumption. Well, I'm not going to worry about that assumption. Okay, so I'm thinking a number of things at once. Maybe I should talk out loud to say some of the things that I'm thinking. So one of the things that we can do is we can split this up using properties of integrals. So I could rewrite this as the integral from -4 to 2 of our function f of x dx, and then I could add on the integral from -4 to 2 of 2x dx, plus finally my integral from -4 to 2 of 3 dx. And given, I mean, we've actually already talked about antiderivatives, and so we could do some analytic methods to solve these, but we could solve these pieces also by taking the just drawing a picture of each of these, and we could find the areas for each of these, and I could do that. The problem is, so this thing, I'm given the fact that the area bounded by the graph of f and the x-axis, this total area is 3, but it didn't tell me that each of the pieces were equal in size, and I'm not sure if that's why things aren't working out correctly. Yeah, and we weren't told the heights of them either. So I feel uncomfortable. If we decided that each of them were equal in size, then we would have these negative values and this positive value, and I would have -2, and then I would have +1, and we would have a total integral of -1. But they didn't actually tell us that those would be equal, and so I don't feel comfortable actually applying that.
That's what I did and it didn't work.
Yeah, you did that and it didn't work. So then it makes me think that maybe we should do something else, but we also don't know the heights of these, so we don't know that if we scoot it up high enough that it'll end up canceling it out. I feel uncomfortable with this problem now that I see it a second time. My assumption when looking at it, I'm going to operate under that assumption and see what happens. It's mathematically interesting even if it's not. So I'm going to assume that these are all equal-sized pieces, because that would give me the fact that this integral would be, so this would be a -1, this would be a, I'll use a different color, that'd be better. -1, a +1, and a -1, because that would give me this integral would be equal to -1. So I'm going to assume that the integral from -4 to 2 of this function is equal to -1. What would that give me? So that would give me a -1 here, plus the integral from -4 to 2 of 2x. I think I'm going to go ahead and draw pictures for each of these as well. 2x is the line with slope 2. And if I go out to 2, this would be at a height of 4. And if I go back to -4, this would be down at 2 times -4, which is -8. So I would say that the area under this part, this triangular piece, is going to have an area of 8 times 4 divided by 2, which is 16. And this chunk is going to be 2 times 4 divided by 2, which is 4. So that would mean that this whole thing would give me 4 minus 16, which is -12. And then this whole piece would be the total distance here. Again, maybe I'll draw a picture for this piece. From -4 to 2 at a height of 3. This is just a rough sketch because I know that this would then be 3 times the distance here, which is 6, which gives me 18. So that'd be 18 minus 12 is 4, minus 1 is 3. It turns out that that's what my computer says is the correct answer. So they did want us to assume that each of these A, B, and C are of equal area, but I don't think that that's very precise because they didn't include that in the problem. So I'm going to say that there's bad wording in this problem, and that we just have to assume that each of these pieces were of equal area.
So what would be the final answer?
So I think the final answer should be 3. I think I'm going to take this integral of -1, and then this chunk of -12, and then this chunk, which was 18. And this number might be different on yours.
Yeah, it doesn't 3.
And it didn't take 3?
Yeah, that was one of the ones I tried.
Ah, because 3, that's what the key says is the answer. So maybe this is an error in the key. I'll look into it. I'll put a little star. I think there are a couple of things that are a problem with them.
3 rather than combining.
Yeah. Yeah. Yeah, that makes sense. Yeah, so I was getting a total of 3.